We want to look at two important operations or two important processes in linear algebra. That's Gaussian elimination and Gauss-Jordan elimination. So suppose we have the system of equations that we want to solve. It's a system of equations and three unknowns. So we begin by gathering the coefficients. Let's do that. So for the first equation, we have 1, that's the coefficient of x, the coefficient of y, and the coefficient of z, minus 1. And we draw a bar here just to get the numbers to the right of the equal sign. All right. Then we have for the second equation, 1 minus 1, 1, then 2. Then we have 1, 1, 1, 6. Now, we want to perform elimination on this so we can solve the equation. So what do? We can subtract the first equation from the second equation and then also from the third equation. So let's do that. It's going to happen by some transformation. So we have row 2 minus row 1. And then we also have row 3 minus row 1. So what happens when we subtract row 1 from row 2? Row 1 doesn't change, so we still have 1, 1 minus 1. We still have the bar, 0. We subtract row 1 from row 2, we get 0 here. Then we have minus 1, that's minus 2. Then we have 1 minus minus 1, so that's 2. Then we have 2 minus 0, that's still 2. Then we have row 3 minus row 1, so we get a 0 here, we get a 0 here. And then we have 1 minus minus 1, so that's 2. And then we have 6 minus 0, that's 6. So if our goal is to solve this equation, then at this stage we can pause. So at this stage we put our matrix in what we call row echelon form, and we call it row echelon form because of the structure we have here, this staircase structure that we have. So the rules for row echelon form are the following. The first rule is that all rows consisting of only zeros are at the bottom. So if we happen to have any row that consists of only zeros, then in row echelon form, it's supposed to be the last row of our system or the last row of the matrix. The second rule is that the leading entry, that is the leftmost non-zero entry of every non-zero row, is to the right of the leading entry of every row above. So the leading entry of every non-zero row. So this is an example of a leading entry. Because this row doesn't consist of entirely zeros, it's a non-zero row. And so the leading entry is the first non-zero element. That's what's called the leading entry. And we are saying that the leading entry of every non-zero row is to the right of the leading entry of every row above. So you look at the leading entry of this row, this is that. Look at the leading entry of this row, that's the minus 2. And then the leading entry of this row is 1. It's saying that the leading entry of this row, let's say the third row, must be to the right of the leading entry of this row. And indeed, it is to the right. And then the leading entry of this row, which is the minus 2, must also be to the right of the leading entry of this row. So that is what it means to put the matrix in row echelon form. Now, why do we care about row echelon form? We care about it because it makes it easier to solve our equation. So if you look at this, what these elimination steps we took have given us is telling us, for instance, here that 2z equals 6. Now, remember this column represents x, this one represents y, and this one represents z. So it's telling us that 2z is equal to 6. Now, if 2z equals 6, then z is 3. So putting the matrix in row echelon form makes it easy to solve the system because once you have a leading entry in a column, you'll see that all the entries below that column are 0. You see that? That's what's happening here. And so it means that once you have a leading entry, you eliminate that entry from all the rows below. In the same way, because we have this leading entry -2, all the items below the -2 are 0. So we've eliminated it from all the equations below. And then we finally end up with the last one, which gives us z equals 3. Now we can put the z equals 3 into this equation. And when we do that, what do we get? We get -2y plus 2z, but now z is 3, and this is equal to 2. What does that mean? It means that -2y equals 2 minus 6. Now 2 minus 6 is -4. So if -2y equals -4, what does it mean? It means that y is equal to 2. So we found our value for y, and we found our value for z. And we can use that to find the value of x by putting y and z into the first equation. So let's do that. We have x from the first equation, x plus y, but y is now 2, minus z, but z is 3, and that's equal to 0. So we want to solve this for x. What does it give us? It gives us x equals -2 plus 3, which is equal to 1. So we have x equals 1. By putting our matrix or our system in row echelon form, we've been able to solve for x, y, and z using a method called back substitution. It's called back substitution because when substituting for the answers, we start from the last variable, which was z here, and then we find it, and then we go and use it to find y, and then we go and use it to find the first unknown or variable, that is x. So just as a review, let's look at the rules for row echelon form. All rows consisting of only zeros are at the bottom. Now, the matrix we used in our example doesn't have a row that has all zeros, but you can imagine, let's say we had 1, 1, -1, 0, and then we had 0, -2, 2, 2. If we had this 0, 0, 0, 0, then the rules say that this 0, 0, 0, 0 must be the last row of this matrix. We cannot have it being the second row. That would be illegal. So let me just show what an example of an illegal one would be. Let's say you had the all zeros here. If you had the all zeros here, 0, 0, and then you had the -2, 2, 2 here, this matrix would not, sorry, I omitted a 0. There should be a 0 here. Yeah, this matrix is not in row echelon form because it violates the rule that says that all rows consisting of only zeros are at the bottom. So when you have a situation like this, what you do is you can swap these two rows. Now, these are the legal operations you can do. You can swap two rows. That is the same as swapping two equations. So when you have a system of equations like this, you can call this equation 1, call this equation 2, and call this equation 3. So swapping two rows is basically a renaming of the equations. So if instead of calling this equation 2 and calling this equation 3, you decide to call this one equation 3 and call this equation 2, that's equivalent to swapping two rows. So you can do that and it doesn't change the solution of the system. That's how come we can do it in the matrix here too. And then the second rule is that the leading entry, what we call the leading entry, is the first non-zero element in a row. So if the leading entry of every non-zero row is to the right of the leading entry of every row above. So it sounds complicated, but it's not. It's saying that when you pick the leading entry of a row, so let's take this row. The leading entry is the first non-zero item. So when you pick this first non-zero item, you go and check all the rows above. And you have to ensure that the first non-zero item of every row above is to the left of this one. So when you take this second row, for instance, this row doesn't have any leading entry, so it's out. But if you look at this row, its leading entry is that, and it's to the left of this one, because this one is in the first column and this one is in the second column. So because this is in the second column and this is in the first column, this one is to the left of this one, or if you will, this one is to the right of this one. So it qualifies. Now let me just rewrite this whole thing again. So we have, let's say we have this system. The system we ended up with 1, 1, minus 1, 0. Then we have 0 minus 2, 2, 2. Then we have 0, 0, 2, 6. The leading entries are this, that, and that. The rules say that the leading entries must be arranged in that fashion. That means that the leading entry of every non-zero row must be to the right of the leading entry of every row above. So this leading entry is to the right of this one, and then this one is to the right of this one. So this matrix is in row echelon form. Now let's look at another process or another method of reducing matrices, that is Gauss-Jordan elimination. And that one aims to put the matrix in what we call reduced row echelon form. And reduced row echelon form is an additional requirement on top of row echelon form. So every matrix that is in reduced row echelon form is in row echelon form, but it satisfies some extra conditions. Now we have here that a matrix is said to be in reduced row echelon form, or RREF, if it satisfies all of the following conditions. The first one, if a row has non-zero entries, then the first non-zero entry is a 1, called the leading one or pivot in this row. So unlike in row echelon form where the leading entry could have any value, it just needed to be non-zero, here we put a restriction that it has to be 1. So if you look here, for instance, in this row, the leading entry was minus 2. But if we want to put this matrix in reduced row echelon form, then we have to divide it by minus 2 so that it becomes a 1. That's the requirement. The second one is if a column contains a leading one, then all other entries in that column are 0. That means that here, after dividing by minus 2 to get 1, we should use that 1 to eliminate everything in this column. Everything in this column. So this 1 cannot continue to be there. It has to be eliminated. And then the third rule says if a row contains a leading 1, then each row above it contains a leading 1 further to the left. So this is the same as what we had in row echelon form. So let's do an example. The same equation as we had before, the same equation we used to illustrate Gaussian elimination. Now we want to use it to illustrate Gauss-Jordan elimination. So again, we collect the coefficients. We have 1, 1, minus 1, 0. Then we have 1, minus 1, 1, 2. Then we have 1, 1, 1, 6. All right, so we can subtract the first row from the second and third rows. So we have row 2 minus row 1, as well as row 3 minus row 1. And what does that give us? Row 1 remains unchanged, so it's still 1, 1 minus 1, 0. Then we subtract row 1 from row 2, so we have a 0 here. Then we have minus 1 minus 1, that's minus 2. Then we have 1 minus minus 1, so that's 2. Then we have 2 minus 0, that's 2. Then we have row 3 minus row 1, so that gives us a 0 here, a 0 here. And then we have 1 minus minus 1, so that's 2. And then we have 6 minus 0, that's that. Now, in Gauss-Jordan elimination, we have to get a 1 here. So the leading entry here is a 1. And the leading entry here is minus 2. But we don't want the leading entry in that row to be minus 2. We want it to be a 1. So what we're going to do is we're going to divide through that row by minus 2 so that that leading entry becomes 1. So we just do a simple transformation. We can get 1, 1, minus 1, 0 as before. Then here becomes 0, 1, minus 1, because now we are dividing through by minus 2. Let me write that. We're basically saying minus half times row 2. That's what we are doing. So you multiply minus 2 by minus half, you get 1. You multiply 2 by minus half, you get minus 1. And you multiply 2 again by that, you get that. So we have minus 1 here. Then you have this one, we can leave it as is, 0, 0, 2, 6. So we have that. Then we continue. So what do? We want to use this leading entry, this 1. We want to use it to eliminate everything in this column, everything in that column. So wherever we have something that is not 0, we want to get rid of it. And that's what we're going to do. So let's see how we can do that. So the first row remains unchanged. Actually, it doesn't remain unchanged. So what we're going to do is we're going to subtract this new second row from the first row so we can eliminate this. So let's do that. We subtract. So let me write what we are doing. We are saying row 1 minus row 2. That's the new row 2. And that gives us 1, 0. Then we have minus 1 minus 1. So that's another 0. Then we have 0 minus 1. That gives us a 1. Then the second row remains unchanged. So we have 0, 1, minus 1, minus 1. And then we have the last row, which is 0, 0, 2, 6. Now we move to the next row and we find the leading entry in that row is 2. We don't want it to be 2. We want it to be 1. So we have to divide through by 2. Let's do that. Dividing through by 2, we get, so basically we want half of row 3. So row 1 remains the same. Then row 2, 0, 1, minus 1, minus 1. And then row 3 divided by 2, we get 0, 0, 1, 3. All right. So what do? We now have the leading entry in the third row being a 1. And we want to use that to eliminate this quantity. So let's proceed with that. The first row remains unchanged, 1, 0, 0. We have 1. Then we have 0, 1. Now, what do we do to eliminate it? We add row 3 to row 2. So let's say row 2 plus row 3. Row 2 plus row 3 gives us this, and then we have this, and then row 3 remains unchanged. Now, this is the end of the process, the reduced row echelon form. So, assuming we wanted to use this reduced row echelon form to solve the problem, how do we proceed? Well, this means that, in particular, the last row here, the third row, means that z is equal to 3. What does this mean? This means that y equals 2. And what does this mean? This means that x equals 1. So one benefit of the reduced row echelon form is that you are able to solve the equation quicker once you have it. It takes more work to generate the row reduced or reduced row echelon form. It takes more work to get it. But once you get it, it's easier to solve problems with it, especially in a situation where you have a square system. That is, you have n equations and n unknowns with a unique solution. If you have the reduced row echelon form, then it's very quick, but it's going to take you more work to get the rref. So in practice, when you're trying to solve problems by computer, the computer will often use this method, that is Gaussian elimination, or the row echelon form, to get it. But because there are fewer computations involved, you can see that after we got the first matrix, that is this one, we only had to get the second one, and then we could get our solutions by back substitution. But this method required us to go through quite a lengthy process. You see many row reduction steps before we finally got to the form we're looking for. However, once you have that form, it's quicker to solve problems. So in practice, we don't really, the computer is not going to use Gauss-Jordan elimination. It's going to use Gaussian elimination. But when you're trying to find something like the inverse, then you almost don't have a choice. You have to do something close to Gauss-Jordan elimination. And that is why we want to learn about it. And then also the Gauss-Jordan elimination produces a unique form of the matrix. So when you have a system of equations, you get a coefficient matrix with a right-hand side, and you perform Gauss-Jordan elimination on it, the result you're going to get is unique, regardless of the steps you take to get there, even though that's not the case in Gaussian elimination. In Gaussian elimination, there are many options you could get. For instance, you can see in this one, if for the third equation, we had divided through by 2, we would have got a result that is also in row echelon form, and it will give us the same solutions as we got. But that wouldn't be a unique representation. So there are many options when it comes to the row echelon form, or what you can get with Gaussian elimination. But the form that you get with Gauss-Jordan elimination is unique. So that makes it special. And there are a number of properties we can prove about it and so on. We can use it in a number of theorems as well. And we're going to look at that in the course of our discussion. See you later.